Good morning, everyone. Thanks for coming. I will finish up this symposium with talking additionally to the MEG, EG, fMRI data we saw by adding diffusion MRI. Yep. So for the purpose of this talk, let's think about the brain for a moment like of a city where we have different streets that are running along the city, and then we can think of brain activity like of cars that run along those streets. So we can then kind of build a model of this brain by connecting the different streets and derive network hubs, for example. So when we think how do we measure the brain when we want to do this non-invasively in humans, we have really limited methods. So we have diffusion MRI, where we measure the number of tracts in the brain, which is kind of equivalent to measuring the number of lanes we have in our street map. Then we have bolt fMRI, where we can measure the bolt signal, which is a really indirect measure. So we can think of that like the gas station. It's kind of correlated to the cars that are running around the streets, but it's not very direct. And finally, we can measure the electrical activity on the scalp. So this gives us a really global measure from neuronal activity, which is kind of measuring the smog of the cars going along the streets, and we need to reconstruct where the activity is actually coming from. So to sum this up, when we're measuring diffusion MRI, we have really no temporal dynamics at all. So the structural connectome will change in months or days. We have a really good resolution of our MRI signal. Then when we want to measure the function, of course we can use fMRI with a good spatial resolution, but of course we cannot get to the real temporal speeds of neuronal activity. So then we can use EEG. There we have the problem, of course, that we put the electrodes on the head, so we need to reconstruct our activity back into the brain, and we lose some spatial resolution for that, but for that we gain some temporal resolution, which is then in the range of milliseconds. And what I'm trying to argue today is we try to put this all together, then we can get a more global view on the whole brain. So the first idea here is to take in a concurrent EEG fMRI resting state recording, to take both the EEG and the fMRI, and then source reconstruct the EEG back into the brain, into the same atlas where we also have our mean bolt activity, and then we can derive for the EEG in the different canonical frequency bands, and for the fMRI using Pearson correlation we can derive functional connectomes, and what is shown there is that those connectivity measures they're correlated between each other, so each dot signifies one connection in one of those connectomes. So what we're currently working on is to kind of measure how this correlation plays out on different data sets from 1.5 Tesla to 7 Tesla using different electrode setup from 64 to 250 electrodes with eyes open or eyes closed. And what you can see here is that in the beta band this relationship is really stable, around 0.3, 0.4 correlation, but it also works for all the other frequency bands. So with this in mind, now we can ask ourselves the question, when we're measuring EEG and fMRI connectomes in the brain, can we use this now to better describe the function-structure relationship of the human brain? So the question we're asking here is when we're characterizing the function-structure relationship, does EEG provide additional value? So the general idea, again, is we put everything into the same atlas. Additionally, here we're using diffusion MRI now, and we're doing tractography, and then we get an additional connectome, which we can then try to use in a linear model to measure the correlations between all those values. And what we were able to show is that we can build with this a good model to kind of explain the structural connectivity. So what we found is that this is of course defined by Euclidean distance, by the interhemispheric connections. Then it is defined by the fMRI, and additionally delta EEG will add additional information to define this relationship. So what you see here is the structural connectivity that we measure by connectomics and the estimated connectivity of our linear model. So now we have those two results, EEG and fMRI. They're correlated between each other, but they provide complementary information when we try to associate this with structural connectivity. So we're kind of seem to measure different connectivities on different time scales. And what we wanted to ask in this study is can we kind of associate this differential spatial relationship by using independent component analysis. So are there any connections that are kind of associated to a different spatial connection between EEG and fMRI? So to do so, we again take our fMRI and EEG connectome for the different EEG frequencies. We stack this all up into one long vector, where we first take the fMRI and then the different EEG frequencies, and then we can put this whole matrix into the ICA algorithm, and then we can derive frequency and subject-specific weights in combination with independent components that are organized like Connectome for EEG and fMRI. So when we do so, what we found first is that we can derive the common part with this approach, where we find that when we order this into different intrinsic connectivity networks, we really find this resting state organization with the visual network, with the default mode network for both EEG and fMRI. When we're looking at the subject and the frequency-specific weights, what we see here is that so each bar of this graph signifies the weight of one subject for the different frequency, and what we see here, we get really a subject-specific weight of this frequency, this resting state trait, but this does not change for the frequency, so the frequency is always weighted the same. In addition to that, we've found a second trait which now is weighted by the different frequency and which is organized spatially different between fMRI and EEG. So what we found is that in fMRI this second independent component is organized mostly in the visual and the somatomotor network, while the weightings of the EEG are distributed across all the resting state connections. This results replicated across two datasets, so this seems to be quite stable. So for now I talked only about static connectivity, so we're taking our resting state data and we're averaging the connectivity of 20 or 30 minutes of resting state inside the scanner. This gives us an estimation, but we don't know if the different timescales we're measuring with EEG, fMRI, are they fluctuating kind of in the same way, or are the fluctuations between EEG and fMRI really a different thing? And the idea here is that we now want to measure the fluctuations of this dynamic functional connectivity by splitting up our signal into dynamic functional connectivity using a 1-minute sliding window, both for our EEG and fMRI connectomes. So what we're doing here is we're taking the time course of this dynamic functional connectivity at each connection, and then we're deriving for each EEG frequency against the fMRI connectome. We're deriving the mutual information. This gives us kind of mutual information connectivity matrix, which specifies the strength between the dynamic relationship between EEG and fMRI. And to test, because of the mutual information, is some kind of random value. We test this against the null model, where we scramble the temporal dimension of the fMRI dynamic connectivity, and then again we compare this to all the different EEG frequencies, and then we compare this pseudo mutual information matrix against our real mutual information matrix. And when we do so, we can find really stable results for all different frequency. What I'm showing here is in 2 data sets the derived mutual information for 2 data sets for the delta mutual information versus fMRI. And what you can see here, it kind of correlates good. It's kind of noisy, but it does correlate. So we can use this method to derive stable values and kind of show that EEG and fMRI dynamic connectivity, when we map this to a 1-minute sliding window, can kind of measure the same dynamics. So those generally this is spread across all the brain, but then we can use those mutual information matrix and compare, for example, the delta band to all the other frequency bands, and then we can derive really specific patterns. What I'm showing here is that for the delta band, as compared to the other frequency bands, the dynamics seem to be dominant in the somatomotor visual connections. So this study showed that EEG and fMRI connectivity kind of show the same dynamics, but when we look a little bit deeper into this relationship, we can derive frequency-specific topographies of this relationship. So to sum up, I've shown that EEG and fMRI on a static view can both measure intrinsic connectivity networks. The different time scales of EEG and fMRI can provide on this static connectivity complementary information, for example, to characterize the underlying structural connectivity. What I then showed is that when we're using independent component analysis, we kind of can extract those complementary patterns by using ICA. And finally, I showed that both EEG and fMRI functional connectivity dynamics fluctuate in the same range when putting them to a 1-minute sliding window. With that, I want to thank all my collaborators who helped me with this work, and thank you for your attention.